Welcome to the 8th module of our masterclass. In this video, we will explore the economics and policy frameworks surrounding CCUS hubs, analyzing shared infrastructure logistics, storage costs, liability, and global carbon markets. It's prepared by Dr. M. Fahed Qureshi from the National University of Singapore. Our learning objectives for this module include understanding the shift toward regional open access clusters, evaluating the cost structure of storage, and analyzing global policy levers like 45Q enhancements and the London Protocol. We begin by examining the development of CCUS hubs and the essential role of shared infrastructure in scaling these technologies. The industry is shifting from traditional, bespoke source-to-sink projects to regional infrastructure clusters. This hub paradigm aggregates multiple emitters, offering economies of scale and cross-chain protection that mitigate the financial bottlenecks often faced by standalone projects. An industrial hub architecture typically consists of 3 stages: capturing emissions from diverse sources, utilizing a gathering network of low-pressure collection pipes, and long-distance transport through high-capacity trunk lines. When it comes to infrastructure, we must consider the, quote, diameter scaling law. Because pipeline capacity grows exponentially, while capital costs increase sublinearly, hubs can significantly reduce per-ton transport costs compared to smaller, individual lines. The Northern Lights project in Norway exemplifies the storage-as-a-service model. By using maritime shipping to transport liquefied CO2 to offshore injection sites, they provide a vital solution for landlocked industrial zones across Europe. In the UK, the Net Zero Teesside and Humber hub demonstrates the potential for massive scale. By aggregating emissions from various industrial sectors, it serves as a template for decarbonization clusters worldwide, targeting up to 20 million tons per annum. Next, we will shift our focus to the economic analysis of these infrastructure projects. Breaking down the capital expenditure, capture and compression processes represent the largest portion of costs, typically 60 to 70%, making them the primary barrier to entry for many projects. Operational expenditures are driven by the energy penalty required for compression, the ongoing replacement of chemical solvents, and the long-term commitment to monitoring, verification, and accounting at the storage site. The levelized cost of storage, or LCOS, is the standard formula used to determine the financial bankability of a storage site. It accounts for lifecycle capital and operational costs relative to the total volume injected over time. Our sensitivity analysis highlights that while discount rates and geologic factors play a role, aggregate volume is the single most powerful lever for reducing these storage costs. Business models generally fall into 2 categories: the utility or transport and storage model, where a regulated entity manages the infrastructure, and the emitter-led model, where companies maintain control of the entire chain to secure credits. Finally, we will examine the critical aspects of risk management and the complexities of long-term geologic liability in these projects. We must address the geologic risks involved in carbon storage, specifically plume migration beyond defined review areas, the potential for caprock breaches due to microfracturing, and seismicity triggered by changes in reservoir pressure. Managing these sites requires a rigorous care window. The initial 5 years focus on plume stabilization. Over the next 2 decades, we verify thermal equilibrium and model accuracy, followed by long-term passive monitoring before formal well plugging and final liability transfer to the state. The Liability Transfer Protocol is essential for long-term project viability. It allows private operators to exit their obligations once they have provided financial contributions to cover state monitoring costs and demonstrated that the storage site is stable and safe. To ensure these obligations are met, projects utilize financial assurance instruments. These include trust funds for decommissioning, surety bonds for potential remediation, and self-insurance protocols reserved for the most creditworthy entities with strong liquidity. Now let's shift our perspective to the global regulatory landscapes that govern how these projects are permitted and operated. In the United States, EPA Class 6 well permitting is a critical step. While the process has historically been slow, recent grants of primary authority to states like North Dakota and Louisiana are beginning to compress review timelines. The European Union follows the CCUS directive, which mandates a minimum of 20 years of post-injection monitoring. It also emphasizes immediate corrective measures for any leaks and links storage performance directly to the EU emissions trading system. International cooperation is also growing. A significant milestone was reached in 2026 with the UK-Belgium Memorandum, which provides a legal pathway for cross-border CO2 transport and storage under the London Protocol. Beyond technical and legal frameworks, projects must secure a social license to operate. This involves deep stakeholder engagement and clear mandates for community benefits, especially when siting projects near overburdened populations. Finally, we will analyze how carbon markets and direct policy incentives serve as the commercial engine for these investments. The U.S. Section 45Q tax credit remains the most powerful incentive, providing robust, long-term support for carbon capture and storage projects, now enhanced by provisions for direct pay and transferability of credits. In Europe, carbon pricing remains volatile but upward trending. The introduction of the Carbon Border Adjustment Mechanism, or CBAM, creates a new baseline price floor for carbon, directly influencing the economics of industrial decarbonization. On a global scale, Article 6 of the Paris Agreement is vital. It enables the international trading of emission outcomes and uses a centralized registry to ensure that reductions are not double-counted between nations. As we conclude this module, we look at the specific requirements for reaching a final investment decision, or FID. Reaching FID is the ultimate project milestone. Success requires obtaining all necessary permits, securing take-or-pay storage contracts, finalizing turnkey engineering guarantees, and establishing a clear pathway to monetize carbon credits. Thank you for joining this module on CCUS Hubs. I am Dr. M. Fahed Qureshi, and I am open to consulting, research collaborations, and technical training. Feel free to reach out via the email addresses or LinkedIn profile listed on screen.